Okay, so during the break, one of your friends asked, what happens if the blind guy is standing on top of a hill? It's a very good question because it is kind of something about the weak side of gradient descent. So it is like, imagine the space is two-dimensional to make it simpler. So because in this example, we are giving a three-dimensional example for the blind guy, but to make it simpler, I'm going to give you a two-dimensional example, but this can apply to any number of dimensions. So it is like a Gaussian hill, you're in the top, and our blind guy is here. So the partial derivative of the altitude with respect to x at this point is actually 0, right? And this guy is 0 then. If this guy is 0, this is, which is a positive value, and it's a positive value larger than 0, this is 0 as well. So there is no update. This is a weak side of plane gradient descent. So if that guy reaches there, even it's at the top of the hill, because he's trying to get to lower ground, remember? He stops. This is something we don't want. That's why actually we don't use the plain version of gradient descent during our optimization. We use a slightly modified version. There are many different versions of the gradient descent, which in the following slides I'm going to be talking about are called solvers. Maybe you've heard about it, which solver you use. Do you use this? What is the solver that you use in your training? The optimization strategy that you use in deep learning is usually called solvers in deep learning libraries. So in PyTorch solvers, when you say, actually you're talking about the version of gradient descent you're using. And in different versions of gradient descent, you have different concepts like momentum. So it is like momentum is, as the name implies, what is momentum in real life? You have rolling ball. The rolling ball has a momentum, has an inertia. It cannot stop. So imagine if the ball was rolling up like this, if it has enough momentum, it will continue to go down because of the previous inertia, right? Because of the inertia, there is no such thing as previous inertia. Because of the inertia. So you add a simple element here, which corresponds to the idea of momentum, which is like a running average of the previous steps you have. This would be a modified version of the gradient descent. Actually, it's called gradient descent with momentum. It's exactly called gradient descent. There are other methods. Maybe the step size you get can be a function of the gradient as well. Just like I said, if the blind guy is on a very steep slope, he would be taking small steps to find some proper place. If it is plateau, he would confidently walk a bit faster. So when you make this guy adaptive to the gradient, make this guy a function of the gradient, then it would be an adaptive way of gradient descent. And if you had the momentum, that would have been an adaptive stochastic gradient with momentum. So like adaptive ADA, momentum M, Adam. There's a solver called Adam. Maybe Adam is that, who knows? So guys, there are different versions of solvers, and we're going to be mentioning them. However, in this course, I'm not going to be delving into details of it. In your projects, when you're trying to solve a problem, you will find a similar implementation, and you will check what kind of solver they use, and you're going to use that solver. Because at the introductory level, deep learning, all you need to understand is this. Okay, there's a gradient descent. You can make the step size adaptive. You can add momentum, and that's it. Because those are parameters too. Okay, let me continue. Okay, so this is gradient descent. Blind guy finding its way on a hill, on a valley, on a place, I don't know. So, okay, how to apply this? Because we are going to be applying this to a neural network. And we don't exactly know what neural network is. The first thing we should understand is how to apply it to the family of networks. The family of networks in mathematics are actually computational graphs. What is a computational graph? What is a family of networks? And what is backpropagation? From now on, I'm going to talk about the method of applying this gradient descent approach to networks of computations. So far, so good. So I'm slowing down. We talked about the score function. We talked about the ground truth. We talked about the loss function and how to find the score function parameters, optimizing the loss function with respect to this strategy. Because instead of random search, we had a strategy, right? So this was a simple strategy. We said there could be better ones, but it's our strategy right now. So now let's take a deep breath and try to understand what neural networks are. If you have taken a neural networks course, that would help. But if you have never taken such a course, don't worry about it. I'm going to be defining what neural networks are. Needless to say, they come from the idea of neurons in our heads. And if you have ever had some curiosity about it, you know that neurons in our brain have some sort of neuron cell, which is called the neuron. And in this neuron, we have two fundamental parts. The cell itself, and this part like an arm, which is connecting itself to another neuron. So this is a neuron, this is another neuron, guys. So neuron is like something, we're connected, we have many as like an octopus, or more than that, we're connected. And these interconnections are actually carry some sort of electrical signals between the neurons. That's the idea. So what is it? What is the relation between this guy and deep learning and neural networks? So the impulses being carried away through axons are the arms, are actually some sort of information passage, some simple bits of information that is like cables of an electric circuit. Artificial neuron is an implementation of this idea. In an artificial neuron, you have the neuron cell, which is this part here. And the arms are some inputs connected to it. Okay, so I have x0, x1, and x2. And actually, each arm has a multiplicative modifier, which we call the weights. And in actual neurons, we also have this. In actual neurons, there is a coating in this axon, which is called the myelin. Maybe you've heard of this. Thicker it gets, it allows more electricity to pass. Because if you've taken, if you're coming from electrical engineering, you know that the radius of the cable is inversely proportional with the resistance of that cable. And if it is thicker, lower resistance, more current flows, okay? So the thickness of the axon is like the value of the weights, because if the weights get larger, since we are multiplying the input coming from that direction, the importance, the effect of that input will be, greater compared to other arms that is reaching this neuron. So the myelin coating thickness is like the weights of that arm that is reaching to this neuron. So this is the neuron that is reached. We are getting different outputs as well. So this is the neurons getting this different neurons. Another one reaching here, another one. Okay. And inside the cell body, things happen. There are neuroscientists who would just speculate it for you like hours. In this course, what we are going to assume is inside the neuron cell, because inside our artificial neuron cell, what we do is we sum up the weighted values, sum them up, add a constant bias value, the bias, get the summation, and feed it to a function, which is an activation function. I don't know what function is that. I'm going to tell you. So it is this function. It could be something I'm going to talk about. So you calculate this and feed it to this function. The output value will be the output of the artificial neuron. This is called an artificial neuron, guys. That's why we call them neurons, because they look like the actual neurons in our brain. So artificial neuron in the end is a very simple score function for some sort of input. There are some inputs, and it's giving an output. So it's like a score function with parameters W and bias B. So it's a score function. If I want this score function to do what I desire it to do, I will need to define a loss function and optimize that difference that loss function provides me with respect to the weights parameters of the artificial neuron. Simple things that you've just learned in this course. And this F, actually I said G, but I always do this. This F is like G, this G activation function, is usually a non-linear value. Because if this is linear, like, multiplication, in that case, a neuron will have no difference than a matrix multiplication. And will provide a linear classifier to you. You know what linear classifiers can or cannot do, because we have talked about them. But difficult decisions, as we've talked about previously, can be done with nonlinear surfaces in multidimensional hyperspaces, feature hyperspaces, okay? That's why this function is usually nonlinear, and in your brain, it's also highly nonlinear. Okay, that's we'll call the function we are going to be using will be a nonlinear function. We'll get there to make the feature hyperdimensional space to have complex decision surfaces. We will need nonlinear functions here. This is the basic idea of neural networks. What could those functions could be? In today's deep learning, mostly in convolutional neural networks, it is this function. So it's a very simple function. If the summation plus bias, this value inside, calculated inside, is negative, then you provide 0 outside. If it is positive, you provide the value as it is. So you are killing the negative ones, letting the positive ones go. This is the most common function that is being used in deep learning today, and it has a very good reason, because it's very easy to take the derivative of that function. Why it is important to take an easy derivative of the activation function, we are going to be talking about it today in backpropagation. But traditionally, the activation function used in neural networks was not ReLU. ReLU was quite an invention of the last decade with AlexNet. Before that, usually, neural networks had these sigmoid or 10H functions, which are bounded, as you can see, bounded between -1 or 1 or 0 or 1, okay? And these had, some purposes of their own. They are still being used in important architectures today, like LSTM, which we are not going to talk about in this course. I briefly talk about in this course. But today we are using LU, ReLU, ReQ, which these guys are actually the versions of ReLU. Still, whatever they are, and don't think about the reasons that we are using them. The reasons, these are the actual activation functions you use in artificial network is they are nonlinear, okay? What would a linear function would look like? What would a linear function look like is if it was something like this. So this is, this is a linear function. So this is a linear function. It's a linear function. This is a linear function. This is a linear function. They're not like that. They are nonlinear. Okay, good. You know artificial neurons. You know what they do inside. Artificial neural networks is like a bunch of artificial neurons connected in some manner, like a graph. So it's a collection of connected artificial neurons. Okay. Actually, which loosely models the connections in our brain, because you see, I'm making a layer representation here. So this is one layer. So this is one layer. This is another layer. One layer is completely connected to the other. The other layer is connected completely to the other. This is like the traditional artificial neural networks. Today's deep learning models are complicated than these, and this is what we are going to learn in this course. However, this represents what happens in our brain, but in our brain, it is like everything is connected to everything. There is not a readable architecture. It's very difficult and complex. But the type of neural networks, the connections in them will be designed. We'll design them for a purpose. So we don't have those kind of networks yet. Everything is connected to everything because we cannot train them. Actually, human brain, everything being connected to everything and is getting trained to this level of intelligence is still a miracle to us. We don't understand how it does. We are trying to emulate that using very simple architectures, like this one. Layers, layers. One layer is completely connected layer, but guys within a layer, these nodes within a layer are not connected, I mean, interconnected within that layer to make the architecture simple. And actually, a very single neuron here actually is actually an artificial neuron. All neurons does this. So all neurons have weights, which are different. So in a neuron, you have some number of connections. This neuron has these number of connections, as you can see. That number of weights. When you sum up all the weights in a network, they become an extreme value. Depending on the scale of your network, this may change, but in today's deep learning, the number of connections, hence the number of weights, and biases, because we also have biases, add up to millions, guys. That's why the problem of optimizing and finding the correct weights is a difficult problem. That's what we are trying to do in this course right now. Okay, and this is traditionally called a perceptron as well. This artificial neuron. So if you ever hear about perceptron, multi-layer perceptron, this is called a multi-layer perceptron. Okay, so these are artificial neural networks, and this is a deep learning course. What is about it? I mean, what is the difference? When you have much deeper hidden layers, as the number of hidden layers increase, we call it deep neural networks. So neural networks was an idea which was there, I mean, for like 60 years. What is about the hype that is going about deep learning? Why didn't make people work on many layered artificial neural networks before the last decade? Because we were not able to train them properly. Until the last decade, we didn't know the mathematical ways to train very deep layered networks. We have found that way, and not we, of course, some guys in Canada did that. And that's why we could create deeper neural networks. And this course is about the story of that. And when there are lots of layers, we simply call these architectures deep. So that's the deepness about deep learning networks, there's nothing else. Okay, so what defines an artificial neural network is, that's core function is, the weights. Each connection is a weight, okay? And those weights actually make up the function, because inside it, you just do this summing and bias. When we apply a function, activation function, we have selected from that menu of activation functions. So the neural network, every operation of our neural network is there. So it looks like transparent, right? But what I always tell you is, they are not transparent. You don't understand what's going on. Well, you can understand every bit of operation. However, the general picture, because there are millions of operations taking place one after another, is difficult to understand. However, every bit of operation is there because we've defined it. We are going to code them. Okay? Good. So each connection represents a weight. The sum is applied to an activation function, which is usually nonlinear, things that we talked about. F is always nonlinear because of the reasons we have talked about. Otherwise, this connection would be a linear system of equations, which will be a linear classifier. If this is a linear function, then this is a linear classifier, guys. Okay, and how to find those weights? We have a vague idea of how to do it from optimization and loss, but how to do this for this guy, and how to apply that gradient descent function to this network. That's a very important invention too, guys, which was done by the 70s, like 50 years ago. I mean, this may sound a bit old to you, but if you check the, history of the humankind, it's quite new. In the 70s, some people worked on applying the gradient descent algorithm to a connected computational graph. This is a connected computational graph. What is a connected computational graph? You start with an input, you make some calculations. The output of those calculations are connected to other calculations. So at each step, you are doing calculations. This is in mathematics called a computational graph. Every neural network can be represented as a computational graph. And some guys in mathematics found ways to apply gradient descent to computational graphs. And that's called backpropagation, which we are going to be talking about next. So computational graphs, that's a way to represent mathematical function in a languageal graph theory. So you can represent any mathematical function in a languageal graph theory. I'm going to do it very simple for you. Then I'm going to skip to more complex examples in my slide. So for example, 2x plus 1. Okay, so x being the input here. So I'm doing a multiplication by 2. Then I'm doing a multiplication by 1. And here's the output. This is a computational graph. The representation of this function using a computational graph. I guess there are no questions. I mean, this is a graphical way of representing a function. Why do I need that? Because this is the only way to understand backpropagation, the implementation of gradient descent to neural networks. So graph theory, if you have never heard about it, I'm sure you did, in a nutshell, is nodes are connected by edges and everything in the graph is either a node or an edge. And in the example I've given, the nodes were the operations and the graphs were the values that are being propagated. And in a computational graph, if you want to find the function, you forward propagate the input through the computational graph. Very important definitions actually, forward propagating the inputs. We are going to use that propagation idea to apply gradient descent in the following slides. Simple example, well, simpler than the one that more complex than the one I've just provided, but still simple. So let the function be x plus y times z. So I've got z, x. So x plus y, summation operation, the inputs are these. Z is multiplied by the output of this guy. This function represented as a graph, a computational graph. Good, simple. ANN is a textbook computational graph, guys. Any neural network can be represented as a computational graph. It is very, it is a good fact because we are going to be applying, understanding ways to apply backpropagation to computational graphs. If we understand that thing, we can apply backpropagation to neural networks. And backpropagation is actually the implementation of gradient descent to computational graphs. So for example, the neural network with 3 inputs and hidden layer. So it is, I have the input x1, so linear ways. This is the bias. So omega 0 is the bias here. So these guys summed up plus the bias plus the activation function. So that perceptron you've seen, this is, can be represented as a computation graph like this. And if we want to make the values the same, so this is, in this case, this is B, and these are the weights. Okay. 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 Nodes are connected by, so ANNs can get complex, more complex, but it never loses its property of being a computational graph. How complex it is, don't worry. It's always a computational graph. Nodes are connected by edges and everything in the graph is either a node or an edge, and we know what is calculated inside. Good. Let's get to the idea of backpropagation. You know what neural networks are theoretically. You know what computational graphs are. You know why ANNs are some sort of computational graphs. You know that ANN as a model is a score function. It provides a score given an input. You know how to define a loss function. You know how to define a ground truth. When you have a ground truth, a loss function, and a score function, you know a strategy to find those weights, which is called the gradient descent. The last step is to apply the gradient descent algorithm to computational graphs. When you understand this, the entire picture of training and neural networks will be over. We were making very fragile steps towards that direction. Backpropagation is short for backward propagation of errors. Which errors? Actually, it is the loss itself. The derivative of the loss, partial derivative of the loss with respect to the weights. We'll see. It's an algorithm for supervised learning of artificial neural networks using gradient descent, just like I said. Given an artificial neural network and an error function, loss function, cost function, error function, the method calculates the gradient of the error function with respect to the parameters of the artificial neural network, just like gradient descent needs to do. But it does it in a sophisticated way so that it's computational friendly. How? So let's apply backpropagation to this computational graph first before doing it for neural networks. So guys, we have this, you remember this computational graph. If the values are this, like this, like this. Imagine I define this as Q to make things simpler for us. I've taken these from Stanford slides. Figures and examples from Stanford slides. You can watch those slides on the video if you need to, because they have a very nice video on backpropagation. Let's check this. So what I'm going to do is, I want to find, for example, let me define, so in this computational graph, my parameters are X, Y, and Z. Okay. I want to backpropagate. No, what I want, before I backpropagate, I want to find the partial derivatives of the loss with respect to those functions, because what I need is this. So imagine there's a loss function. Say loss function is something. What was the loss function? So absolute value f minus g, remember? And f is this guy, okay? So f had some parameters inside. So these are the parameters. In gradient descent, remember what you needed was with respect to the weights, theta in this case, or x, y, z. So what I want to find is partial derivative of the loss with respect to this x, y. And loss is calculated here. There's a loss here, right? Loss function. So what I have here is partial derivative of the loss with respect to the partial derivative of the loss, 1. I need to find the partial derivative of the loss with respect to, so what I want to find here is partial derivative of the loss with respect to f. What I'm going to do is I'm going to backpropagate this partial derivative using the chain rule of calculus for derivation. How? It's a bit strange, but you're going to get there, don't worry. Now, f, so we have the derivative of f here. What I need is, I want to find this guy. This is the loss, think of it. So what is the partial derivative of f with respect to z? How can I find it? I can define it as, sorry, let me get there. Do I have it in my slides? Yes, let's do it for Q now, first, not for Z. Sorry about that, let me get there. I'm trying to remember my own slides. Let me get my pen. Now, what was f? The guy makes a simple definition here. Instead of x plus y, it uses q. So the function becomes q times z. So what is partial derivative of f with respect to z? If this is the function, it is q, right? Any questions about it? No. So if at this point q is 3, the partial derivative of with respect to z is 3. Any questions about it? So similarly, I'm trying to find the partial derivative of x with respect to y. First, I'm going to find the partial derivative of f with respect to q, then jump accordingly. Let me clear them. Get my slides. So it is 3. So it is the same thing. I'm going to do the same thing. Partial derivative of f with respect to q is z, right? Because f was q times z. If you take the partial derivative of this function with respect to q, you will have z. In that case, z was -3 here. So the partial derivative of f with respect to q is 4. Okay. Now I need to find partial derivative of f with respect to x. What I have is the partial derivative of f with respect to q. If I have the partial derivative of q with respect to partial derivative of x, these will cancel out and I will have this, right? So I have this, which is -4. But I need to find this. What was q? Q is x plus y. Let me find the partial derivative of q with respect to x. This is the constant dead, so 1. So this is 1, guys. So it is -4 and -4 again. Backpropagation is a way to find the partial derivatives in a backward manner in a computational graph for a given value of inputs for that computational graph. For different values of input, the backpropagation values would have propagated at different values. This is a funny sentence, but you understand what I mean. So this is backpropagation. You can apply this to any computational graph. So it is -4 and -4. When you apply this to a more complex function, nothing changes, nothing. So this is a sigmoid function, guys. This is a sigmoid function. And it's one of the activation types. So I'm applying it to an artificial neuron now. So I have 3 inputs. I have the bias. And when I apply this, I apply an activation function. So in this case, I have 3 inputs. Maybe the bias is 0. The bias is omitted in this example. You multiply them with the weights. This is the bias, I'm sorry. This is the bias. As you can see, there is no multiplication. You sum them up. You add the bias. And you apply the sigmoid function. What you do is you first make it negative because this is the x here. This becomes so it's the sigmoid function. Because let me just, so this sigmoid will be and the weights plus the bias, omega x plus the bias. So this is the x here. So the output here is called x. First I get the negative of it, the exponential of it, add 1, take the reciprocal of it, and I get sigmoid function. So if you know the analytical derivation of each element here, you can backpropagate the partial derivative in a backward manner. There is nothing stopping you from that. So in a computational graph, if you know how to take the derivative of each node, you can backpropagate the derivative given the values for given the input values. This is called backpropagating the derivatives in a computational graph. I have still combined it with gradient descent, guys. I am going to. The first thing I need you to understand is backpropagating the derivatives in a computational graph in a backward manner. Okay. So we can generalize this. Whatever is inside, if I can take the derivative of this guy, I can backpropagate the errors. So simply what I need is the backpropagation of z with respect to x, if this is what I need. And if I have the loss of the partial derivative of the loss with respect to s, but I need the partial derivative of loss with respect to x, for example. So I will use this function. And z with respect to, so I know this, I've got this, I need this, then I need to find this. If f is a function like this, so f is a function like this, then, and if I know f, I can calculate this, right? If z is x plus y, then partial derivative of z with respect to x will be 1, just like the previous example. So in a block, if I know the analytical gradient of the input-output relation, and if I know it for all the blocks in my computational graph, I can apply it. I apply backpropagation, to that computational graph. Okay. And look. So gradients, same for the y components. And as the network gets larger and larger, I can do this. And in these examples, I have given x and y as single components, but they can be vectors. When they are vectors, these partial derivatives are called Jacobians. You may remember this from linear algebra. When it's a Jacobian, it's a vector of partial derivatives, like the partial derivative of the loss with respect to x1, then x2 vector. That's called Jacobian. Okay. Actually, if z is also a vector, it's a matrix. Partial derivative of z1 with respect to x1, partial derivative of z1 with respect to x2, the row, then partial derivative of z2 with respect to x1, it becomes a matrix if they are both vectors. Okay, that's called the Jacobian matrix in mathematics. Good. So in vectorized operations, what you get is you get a partial derivative. There's a block inside. You get a Jacobian matrix. So the output vector is some value. So the input vector is some value. In that case, your Jacobian will be the input times the output vector because it's a partial derivative with respect to. This is an important slide. Stanford guys had this because while backpropagating, this is the partial derivative matrix you need to keep in the memory of the computer. And the input-output relations, you have 4,000, it's a very common number. And you can come up with these numbers, and you'll come across these numbers in deep learning. So this matrix will make a very large matrix, right? These are very large matrices you should keep in your memory while you are doing these calculations. And actually in deep learning, we do these calculations in GPUs. That's why we need GPUs and we need very high GPU memories while we are doing these calculations. But we are going to get there. We are going to get how this is exactly implemented. So at this point, we know backpropagation as well. You know how to backpropagate the derivative in the backward direction in a computational graph. The last step is applying the gradient descent. Because actually applying the gradient descent using backpropagation is updating those weights one layer at a time. I repeat, applying gradient descent using backpropagation to a neural network is updating the weights one layer at a time. How? So in training, we'll need two steps, the forward pass and backward pass. Why do we need the forward pass? Remember, in backpropagation, you first needed to calculate the green values, the forward values. Then you could calculate the backward values according to the green values and the partial derivatives, okay? So we did the forward run, and in the backward run, we used these green values and the derivatives for that. Okay, so in training, finding those weights, the first rule is we need to forward pass network, calculate a loss, backpropagate the partial derivative of the loss with respect to the parameters, and update the weights. So this is called, actually, this is forward and backward pass. What it looks like this is like a code system overview schematics. So this is, these are the layers, so layer 1, layer 2, layer 3. And in this presentation, the layers are these. So layer 1, so input, layer 1. So there's a these are the weights. Input 2, the weights, and input 3, and you have a loss function. So you calculate the forward pass, calculate the loss function, and backpropagate the weights. And while you're backpropagating, at each layer, you apply the famous formula of gradient descent. That, remember, old man's location new equals to old man's location old minus step size lambda plus the slope, multiplied by the slope, not plus. Okay, so how it is done for neural networks is this whole thing that simulates the backpropagation algorithm, doing it layer by layer, applying gradient descent to each layer, using optimization, getting the weights. These whole systems in deep learning libraries are called solvers, okay? The solver kind of orchestrates that, kind of manages everything for optimizing the necessary parameters for your model. It does the forward and backward pass. So the forward inference and backward gradients to form the parameter updates. The responsibilities of learning are divided between the solver for overseeing the optimization and generating parameter updates, and the net for yielding loss and gradients. So you have a network, the solver and the network does the training procedure together. We still didn't get to the point where everything is updated. I'm going to. So solver scaffolds the optimization bookkeeping and creates network, because we are going to do it iteratively. Remember, old guy moving iteratively. Solver will control the whole network's old guy movement. So it's going to do the forward run, then calculate the loss, then get the partial derivative of the loss with respect to the final layer parameters first, update the final layer, backpropagate the loss, update the previous layer, backpropagate the loss, update the previous layer. And this operation is done iteratively by that box called solver. So it's implementation of the optimization algorithm in your code. Various types of solvers exist. They kind of implement different versions of gradient descent. Stochastic gradient descent is a gradient descent when you calculate the loss for more than one training sample. So you get 10 training samples together and calculate the total loss. It's called stochastic gradient descent. So there are many different methods when you apply momentum, when you make the step size adaptive. These are different methods and different implementations. I'm not going to get into the details of them, because for all solvers, the idea is the same. We'll be updating the layer parameters one by one, okay? And I'm going to get there. Stochastic gradient descent is a simple version of gradient descent where you have the loss calculated not only for a single element, but a number of batches. They are called batches. In deep learning, you've heard of them. What is the number of batches? And actually, since all of these things are done in GPU, the number of batches in a stochastic gradient descent is decided by how much training samples you can fit to your GPU memory, okay? So it's a vanilla mini batch gradient descent code where you have sample training data. You have 256 samples. You evaluate the gradients and you update the gradients in this sense. You see in Python, this is weights new equals weights old plus the step size lambda times the grades gradient, which is the partial derivative of the loss with respect to the weights. Okay, so there's a term here which you may not recognize. This is the loss function, and this is the, so what you have multiple batches, right? Each sample will create a different loss. The score function will create a different penalty for different sample, because each sample, there's a pale, there's a reddish apple in your set of 256 samples. There's a greenish pear. They will have create with that state of the score function different penalties. You sum up those penalties. That's why there's a summation of losses here. However, there's another parameter here, a function R, which we have never talked about. That's called regularization. Regularization is an idea in optimization which helps you to train the system, okay? Good. Let's talk about regularization in the next hour, but before I finish, if there are questions, I'd like to answer them.
Hocam daha deminki notasyondan ben bir soru soracaktım da. Gradient V deyince tam ne demek istiyordunuz?
Gradients?
Gradient V, Eli, X, Y'yi V deyince.
In which slide are you talking about? Which slide?
Daha deminki hocam.
This one?
Evet, this one.
Okay, so are you talking about the pseudocode or are you talking about here?
Şu sembolü anlamadım. Yani gradient V, Eli, X, Y'yi V sembolünü anlamadım.
Here in the figures, or you're talking about
in the formula, below formula. Bir altlık formula.
This one. So you're talking about
formula.
Yes.
Gradient W. Evet.
A gradient W. This gradient W. Yes. Well, it's what we are trying to do is this is the loss function. We are trying to calculate the partial derivatives of the loss function with respect to the gradients. So it is like when you're finding the partial derivatives of the loss function with respect to the weights, you are taking the partial derivative, the gradient. That's what it's doing. You're taking the gradient, partial derivative of the loss. So that's nothing else. Another mathematical way of showing taking the partial derivative of the loss with respect to the weights. That's it. Okay?
Yani o şey işareti mi? Partial derivative vektörü işareti.
Yes. Exactly.
Tamam.
So this is the loss function actually. But there is this regularization factor which we are going to be talking about. Any other questions?